Okay, so I hope you can hear me. Good evening and welcome back to the Asset Colloquium today. If there are some, and I can see some of you who are not from the TIFR family, ASSET stands for Advances in Science, Engineering and Technology. We mainly organize colloquia like similar to what you are going to hear today at every Friday at 4 o'clock, dealing with most of the time experimental sciences in general, the detectors, the instrumentation, electronics, sometimes medical technology, software, and similar fields. And today we have a very interesting talk lined up for you. Search for lightly ionizing particles. This is going to be given by Professor Bedanga Mohanty from NISER, Bhubaneswar. I know he in general doesn't require any introduction, but in case some of you who have happened to join from colleges other than generally are known in the in this high energy and nuclear physics, let me, of course, I can't really do justice in introducing him properly. Then half of the colloquium time will go for me. So let me just quickly run through. Bedanga Das Mohanty is a professor of physics and Dean of Faculty Affairs at the School of Physical Sciences, NISER, Bhubaneswar. Recently was also Scientific Associate at the Experimental Physics Division at CERN, working in ALICE. He is a member of the Super CDMS collaboration for dark matter research. Many of you, I'm sure, know about this. Bedanga Das did his master's from Utkal University, Bhubaneswar in 1996 and PhD from Institute of Physics, Bhubaneswar, 2002. And he was a postdoc at Lawrence Berkeley National Laboratory, USA. He was at the VECC, Variable Energy Cyclotron Center, Calcutta, from 2002 to 2012. That's more than 10 years. And he won many awards and honors. That's what I said. It's very difficult to do justice to even list all of those. Some of them are J.C. Bose National Fellowship, Fellow of all 3 National Science Academies, Fellow of the American Physical Society, Bhatnagar Prize, Swarna Jayanti Fellowship, DAE Outstanding Research Investigator Award, DAE Young Scientist Award, INSA Young Scientist Medal, and so on and so forth. He is the editor of the International Journal of Modern Physics. So with those few words of introduction, now it is time to hear from Bedanga on this very interesting topic.
Thank you, Dr. Satyanarayanan, for this kind words. Let me share. Yeah. Okay. So thank you for inviting me to give this talk at ASSET Colloquia. The title of the talk is Search for Lightly Ionizing Particles. This is within the Super CDMS collaboration. The work is mostly done by the PhD student who has now submitted his thesis, Samir Banik. This work appeared last month in this paper. Before I move on to the talk, let me just define what is this lightly ionizing particles. All of you know that when a charged particle passes through the matter, it loses energy. The energy loss per unit length is given by this Bethe-Bloch equation, which is on the right-hand side. And of course, it was modified to include the relativistic corrections. You can see that it depends on the square of the charge of the incident particle. And so we are talking about fractional charge particles. So the energy loss will be smaller compared to particles which have integral multiple of charge of electron. And that's why we call it as lightly ionizing particle. This field is new to me. I'm still learning as we move in this experiment and try to look for rare events, such as look for lightly ionizing particles. So to start with, just a brief recap recapitulation of standard model. We have 4 basic interactions in nature, and 3 of them find a place in the standard model of physics. Strong interactions, which leads to quark and gluons being confined inside protons and neutrons, or hadrons in general, or protons and neutrons forming nuclei. Electromagnetic interactions, these are the interaction between the charged particles. For example, electron and the positively charged nucleus forms atoms. Weak interactions, as an example, is the phenomena of radioactivity. Now, it has a set of fundamental particles which constitute the visible universe. There are 6 kind of quarks, they're antiparticles. There are 6 kind of leptons, and they're antiparticles. Then there are force carriers, the W+, W-, Z0 bosons, photons, and the gluons. And on 4th July 2012, the Higgs boson discovery was announced, through which we think we now understand how these fundamental particles acquire mass. Now, if you look at the charge of these particles, this is given on the table on the right-hand side, taken from this review. We have charges on these leptons, neutrinos, W. These are sort of directly observed. Then we have fractional charges carried by the quarks, where the charge is the charge of the electron, about 1.6 into 10 to the power minus 19 coulomb. These are deduced from the properties of the hadrons. And then there are particles which are not yet discovered. For example, dark matter, where we expect them to be neutral particles. Otherwise, if they would have undergone electromagnetic interactions, then possibly would have detected them if they exist. So that is about the charges of these fundamental constituents of visible matter. Before I go to beyond why we need to go to beyond standard model, let me just recapitulate this charge of electron. This was measured using what is called as now Milliken liquid drop method using Stokes' law. Now we have a charge Q, and it's subjected to an electric field, and we can use Stokes' law, which depends on the property of the fluid and the terminal velocity attained. I will show you in the next slide. And there is a way to determine this capital Q, which is the charge on the drop. And that is how it was done for the Milliken liquid drop method. So let me go to that description. On the right-hand side is the experimental setup in the NISER undergraduate lab. You can see there is a red one, that is the atomizer, which you will see in this video. And we try to measure the falling and the rising movement of a charged oil drop in an electric field of the capacitor. Basically, one measures the falling velocity and the rising velocity in the electric field. And if you know the capacitor voltage, then solving the balancing force equations, one can write the charge as given in this middle box, where C1 are some constants which depends on, for example, the inter-electrode distance, or the densities, acceleration due to gravity, and the viscosity. There are other ways to deal with it, like using Helmholtz coils, but okay, I'll not go into that. But I found a nice, just a very short video on the principle by which this was detected. So let me play it. And this is regularly done in the UG labs.
In a series of experiments carried out between 1908 and 1917, R.A. Milliken succeeded in measuring the charge of the electron with great precision. In his experiment, a fine mist of oil was sprayed into the upper chamber with an atomizer. Some of the tiny oil droplets fell through the hole in the upper floor, and Milliken was able to determine the mass of an oil drop from its terminal velocity. Next, Milliken used an X-ray source to ionize gas molecules in the chamber. Electrons from this ionization process adhered to the oil droplets. The oil droplets now carry a negative charge. The negatively charged oil droplets can be halted by adjusting the voltage across the two plates. As the voltage across the plates is increased, the velocity of the oil drops slows. As the voltage is increased further, some drops will begin to move upward toward the positive plate. If the voltage is set just right, an oil drop can be suspended. When an oil drop is suspended, its weight, mass times acceleration due to gravity, is exactly counterbalanced by the electric force applied. The electric force applied equals the applied electric field, E, times the charge on the drop, Q. Since the mass of the oil drop, the acceleration due to gravity, and the applied electric field are known, Milliken could solve for Q, which is the charge on the drop. Milliken found that droplets had different charges, but each was a whole number multiple of a smaller charge, equal to negative 1.60 times 10 to the negative 19th coulombs.
Okay, so that was a quick recap of the basic unit of the charge which we measure. Now, let me come to the topic of interest by saying that there is need to go beyond standard model across different fields. For example, in cosmology, we need to explain matter-antimatter asymmetry, account for the accelerating expansion of the universe. The standard model as it stands doesn't have a predictive power for dark matter candidates. In the area of force and unification, there are also open issues, but for this talk, we are dealing with some things related to particle properties. One, of course, which all of you know, are the masses of neutrino and neutrino oscillations are not accounted for. Similarly, there is also no explanation of electric charge sort of quantization. So we cannot explain why electric charges of the known elementary particles are 0 or plus minus Q. Q is 1.6 10 to the minus 19 coulombs, or 1/3 of Q or plus minus 2/3 of Q. The quarks combine into composite particles such as hadrons, and then they carry charge which is sort of integer multiples of Q, and can take up values 0, plus minus 1, plus minus 2. So all observable particles that we see have this 0 or integer charge in terms of Q. So that is the basic idea. If I put it in the set of exciting discoveries, just a selected list, it is an interesting search for these fractional charge particles. In this list, for example, the Higgs boson, whose existence is now confirmed, and through the properties are getting measured with higher precision, from which we have come to know about masses of fundamental particles. The gravitational waves, its existence has been confirmed, and it supports the general theory of relativity. But there are many, many unknowns yet to be discovered, like the nature of this dark matter particle, antimatters, proton decay, magnetic monopole, which could lead to electric magnetic charge symmetry, and similarly, the fractionally charged particles, which is today's topic. Its existence is not yet confirmed. Why particles have this integral multiple of charge carried by an electron. So that is basically why we got interested in looking for it. Now let me just clarify that after the discovery of this measurement of the charge of an electron 100 years or so, there has been several searches for fractional charge particles. But in 1960s, it sort of got modified as we came to know that free quarks are always confined inside hadrons, which are baryons or mesons. Baryons are like 3 quark carrying, valence quark carrying hadrons, or mesons which has a quark and anti-quark. This is because of this we understood from the phenomena, from the theory of quantum chromodynamics. If you look at this middle plot, it shows the strength, the coupling, strong coupling constant as a function of momentum transfer between, say, 2 quark or a quark and an anti-quark. And if you go to smaller momentum scales, or as per uncertainty principle, larger distance scales, then this alpha S value increases, so making it very difficult to deconfine. Of course, looking at a deconfined system of quark and gluons is itself a field, but that is not what we are looking for. In these searches, these are searches for fractional charge beyond looking for a free quark in the system. To address the basic question is, what is this natural law for this simplicity that particles have some n times q or f times q, n times q, and why not some fraction of the charge carried by the electron? Just to complete, these two figures are on the right hand side, reflects indirect sort of evidence of existence of these patterns from these dijet and the trijet events. Now, if you ask me that is there some theoretical support for such fractional charges, there are some theories which tend to suggest like the grand unified theories or their extensions, supersymmetric theories, or dark matter models. They allow for having charges, fractional charges, and that is sort of the theoretical support we have. Now, what could be the sources of these fractional charge particles so that we can try to detect in experiments? One source is production in accelerators or colliders. As given in this review, these are some of the processes by which this can be produced, like protons colliding with nucleons or electrons, even heavy ions. Search has been done in heavy ion collisions also. The only thing is the mass of such charged particles are limited. The search range is limited by the energy of the collision. Now, there could be sources of production outside Earth. For example, very early universe, they may have been formed and now they got some embedded inside some material which we can find in present day. People have tried to look for these fractional charge particles in meteorites, for example. Then particles could be produced through some violent astrophysical processes or through cosmic rays interacting with Earth's atmosphere. These are the sources which we tried to explore in our study. There is another interesting area of looking for fractional charges in bulk matter, which it's not I'm not the expert in that, but what I've read is that there are studies involved for looking at fractional charges in bulk matter, such as a negative fractional charge particle could be held in a bulk matter by the Coulombic attraction of the nucleus. If they are heavy, and as the Bohr radii goes as 1 by the mass is inversely proportional to this mass of the electron, so you could expect a lower Bohr orbit. This orbit may be so small that the nucleus and this fractional charge particle may form a compact object. If it's a positively charged fractional charge particle, then it may act as a nucleus collecting electrons and being held together in the solid by molecular forces. So there are some activities looking for such bulk matter, such as for fractional charge particles. Now, what is some of the challenges involved in looking for this FCPs or fractional charge particles? All the techniques that we have used in past or currently we are using, these require that these particles are isolated during the measurements. For example, that's the reason why we are not able to directly measure the charges of quarks. So same holds. Now there are two unknowns in this search for fractional charge particles. Of course, they carry charge, so their interaction is electromagnetic. That is what most of the experiments exploit, but we do not know if such particles, if they exist, can they interact through other kind of forces. That leads to some uncertainty in their production cross-section, because that depends on interaction and also on the detection principle. Further, we do not know about their mass. As I mentioned a little earlier, that if you are looking for these searches from cosmic rays or colliders, then the center of mass energy allows you to look for a very broad spectrum of mass. So in the phase space of charge and mass, a lot of things are unknown. So these are the three dominant ways where people try to look for these fractional charges. I will show you some of the results from these searches, except for the bulk matter. In the accelerator-based searches, there has been search in the electron-positron collider and proton, antiproton colliders also, and even heavy ion collisions. The center of mass energy and the collision systems are given in this table. You can find them in these reference papers on the lower left-hand side. All of them have resulted in null results. From the cosmic-based search experiments, what are shown are the experiments in the table and their sensitivities in terms of the intensity or flux of these fractional charge particles. Let me concentrate on the lower right-hand side plot. The x-axis is the fraction of charge carried by the particle relative to the electron charge. For example, 10 to the power 2 means we are looking at a possibility of a fractional charge particle which has charge 100 times smaller than that of electron. The y-axis is the intensity expressed in units per unit area, centimeter square per second, and per steradian, the solid angle. And the experiments which have ruled out the presence of such fractional charge particles, the curves are shown here. Let me just take an example. For example, if you look at x-axis 10 to the power 2, and if you go to the y-axis, it is, I think, roughly 10 to the power minus, say, 9. So a fractional charge particle with a charge 100 times smaller than the electrons, if they exist, then their intensities has to be less than 10 to the power minus 10 per centimeter square per second plus per steradian. So that is what this current limits before our measurements revealed. So now let me move to the measurements which we did. This summarizes the search phase space, but it's slightly in a different x and y axis. X axis is still the fraction of the charge relative to electron, and y axis is the mass. What are shown here in different areas and colored bands are many different kind of experiments, colliders, astrophysics related experiments. What is the search space? And this central box, which is here with written CDMS light, is the space which we try to look at in the super CDMS experiment. It expanded from the fraction of charge carried from about 10 to the power 2 to about 10 to the power 7 times, so 10 to the 8 times smaller charge compared to electrons, and the mass is also as indicated in the y-axis. So it's a large phase space we were able to cover because of the low threshold and better resolution of the detectors which these experiments have. Now, the experiment is Super CDMS. This took data in 2003 to 2006. It's an underground-based laboratory in the Sudan mine in Minnesota. It has an overburden of 713 meters. Now, in order to compare each of these overburden has many different kind of materials, rock composition. So in order to compare across experiment, it is better to express in terms of meter water equivalent. And that was about 2090 meter water equivalent. And it allowed a lot of reduction in the background to about 1 per kg per year. This, of course, a new version of this experiment is being now constructed in Snow Lab, that is in Canada. And so this is the older version of the experiment. There are germanium and silicon crystals are used as detectors, about 30 of them. 6 of them are arranged in a tower, and then they are further shielded to protect them from backgrounds, dominantly gamma backgrounds. And there are also ways to veto muons, cosmic muons, in order to remove them. Typically, these detectors are about 7.6 centimeter in diameter. Height is about 2.5 centimeter and thickness 1 centimeter. They operate in 2 modes. One is high voltage mode, about 70 volt, and the other, which we label as IJIP, usually operates in around 4 volt. Both has its advantages. The high voltage mode allows for lower threshold operating of the detectors, whereas the IJIP mode helps in getting a better signal to background performance. Now, a little bit more on details of this experiment. This is, as I mentioned, is underground, but there are various other components. Broadly, the detector volume is inside this green shaded region. It's a cryogenic detector, so it's cooled by using a dilution fridge. And additional coolings are required also. You can see from the top how the detectors are arranged, or a cross section on the top right, and on the lower right is sort of a cross-sectional view. And these are mounted on a spring-loaded platform for seismic isolation. Now, how does these detectors function? So when a LIP, like lightly ionizing particle, interacts with this detector, which are semiconductor detectors, then you expect that it will either interact with the electrons scattering, which would give dominantly energies through ionization mode, or it will allow the nuclear recoils to happen, where energy is dominantly via phonons. So let's take, for example, there is a recoil of the nucleus of the detector material. So there is a primary phonon energy. Now, when the charges in the crystal starts to move, there are other, and the detector is of course given a bias voltage, then there are other phonons generated, which one calls as Luke phonons. So what one measures in this detector is the total phonon energy coming from the primary recoil energy, as well as from these Luke phonons, which depends on the number of electron hole pairs created times the voltage, of course, the charge and the voltage applied to the detector. Now, what happens is these signals are taken from through a superconducting tungsten transition age sensors. These are operated at the critical temperature of this material. and that is around 40 to 50 millikelvin. That is where it is kept. Now, when the particle comes and there is a nuclear recoil, as a result, there is energy deposited, and as a result, there is heat generated. That's what leads to these phonons, and then the resistance changes. So, so the detector is operated at around this TC, and as soon as there is deposition of energy, the resistance changes. Of course, there is an electrothermal feedback which returns the transition age sensors to its nominal operating resistance. Now, the deposited energy is just the integral of the deficit in joule heating, which goes as V square by R, which led to this increase in resistance, and that is what is captured. Typically, the mass of these detectors is around 600 gram each unit, and there are 4 channels. There are 4 phonon channels, and there are 2 charge channels on these detectors. And as I mentioned, they can operate in 2 modes, low voltage and high voltage modes. So just to show you how typically the pulses look like, now there are both phonon and ionization signals. On the top plot is what we show the phonon pulses. This is ADC in the y-axis and time in millisecond in the x-axis. There are 4 different kind of sensors. So the signal seems to have occurred on the zone B. That's why the the signal strengths are higher. And below are the ionization pulses. Now, one can then use the ionization yields and the phonon yields in order to construct a ratio to separate whether the event happened a consequence of electron recoil or the nuclear recoil. And that is what is shown here on the bottom plot, the ratio. And one has verified that this works by using an electron source, beta source, and neutron source to show that one can separate out these 2 kinds of recoils. Now, coming to our search strategy, what we did was to put a 90% confidence limit on LIPS. So on the left-hand side is the intensity of LIPS, which is, by the way, a function of the charge of these fractional charge particles, its mass, as well as its beta gamma. Beta is just velocity by the speed of light, and gamma is the gamma factor, roughly corresponding to the momentum of these fractional charge particles. Now, in order to get this intensity limit, one has to find out the number of such LIPS with 90% confidence, and then you divide it by the remember, this is per unit per centimeter square per second per solid angle. So you divide it by the lifetime of the detectors. On the lower left-hand side is the data taking sort of period for the CDMS light run. And so it was from the February to July data set. We had about 97.81 days of data taking, which is about 84.6% of the full run, the second run of this detector. The rest of the data was used for the blind analysis to get our codes ready to be applied on the real data. What one would need is the next quantity of course, there is a geometrical factor corresponding to the area exposed, but then one would also need to correct for these observed counts, which are obtained by applying some selection criteria, efficiency times the probability distribution functions of LIPS depositing energy in the detector. This is the probability distribution function, again, depends on the charge carried by the fractional charge particle, its mass, its beta gamma, and the angle, and so on. So in order to arrive at the limits, we not only need this number for 90% confidence, for which we need the events as well as the background. We need the probability distribution function and these efficiencies. Okay, so then, so what we found is there is a lot of ambiguity in this getting the probability distribution functions. Normally in high energy experiments, particle physics or nuclear physics, we usually look at the probability distribution of charged particles by simulating them within a geom framework, which has the material and the geometry of the detectors. No such thing was available for the LIPS. So what Samir and the group started doing is trying to modify the geom routines to incorporate the fractional charge particles into the detector simulation package. For example, on the left-hand side is the typical energy loss per unit length as a function of momentum for muons in germanium. And you can see how this energy loss varies with the momentum or the beta gamma of the muons. At the lower energy region, it is dominated by ionization contributions, whereas at higher beta gamma values or higher energy, it is dominated by radiative contributions. And radiative contribution further has contributions from Bremsstrahlung pair production and photonuclear processes. So all these aspects has to be simulated in order within the geom framework in order for us to proceed with the data analysis. So that is what was done in this simulation paper, and the codes are publicly available in GitHub, so that if anybody is interested, one can use these codes for simulating these fractional charge particles. Now it's just not simulation, we have to validate the simulation. I'm not showing all the validation plots, but some of them are shown here. For example, we know that the stopping power goes as square of the charge of the incident particle. So, so we simulated, put all the processes properly in place and try to see if we get it back and compare it with muons on the top left-hand side, and it satisfied the criterias. We also had to modify a few things in the pair production and Bremsstrahlung part of the codes. Remember, LIP mass impacts the expected energy deposition distribution through Bremsstrahlung processes, and the number of Bremsstrahlung interactions is proportional to the inverse square of the LIPS mass. So that is what you see in the bottom right-hand side plot. And so all these validations were done and to prepare a framework so that we can get a probability distribution function from the simulating the detector material and the geometry of the detector which we are using in order to proceed forward. So then we have this, finally, the probability as a function of energy deposited by LIPS. On the left-hand side is a variety. As you can see, there are many different kind of parameters. One is beta gamma, one is the fraction of the charge carried. And also the angle of incidence, you can take it isotropic. We also, that is one aspect we considered. The other is cosine square theta type of distributions which cosmic muons follow. I will break the left-hand side plot into two simpler points to make my point. On the right-hand side top is the probability versus the energy deposited. You can see that the beta gamma values are kept fixed, and the charge of the fractional charge particle is varied, and the probability reduces with decrease in charge of the fractional charge particle. On the lower right-hand side plot is the charge is kept fixed and beta gamma is changed, and you can see larger energy deposition are more probable for smaller beta gamma values. And just to give you an idea of the total probability of energy deposition for the different curves on the left-hand side, is represented by the value of P, which comes in our analysis range. Okay, these are the typical probabilities that of the energy deposition within our analysis range in the CDMS slide. So with this PDF in place, now we looked at the data. Data, as I indicated in the beginning, you have a pulse coming, you have a noise. We then pass it through through what is called as an optimal filter, which gives us the energy content in the pulse. You apply calibration to convert those into sort of energy equivalent units. And then you get this distribution in the middle of this page. Then you apply quality cuts. For example, how good is the raw pulse? Some veto criteria. You would like to choose the fiducial volume properly so that you have least corrections. Then trigger efficiency. The experiment was concurrently for some period running with the Minos experiment. So we tried to avoid those period of data taking. It could be a source of background. So after that, one gets this energy deposition spectrum in the middle from the data. Now, we have applied a set of selection criteria to obtain these distributions. We need to correct for the efficiency of this selection criteria. For this, we had to generate from the data itself a set of fake events by taking the signal pulse and the noise pulse and try to combine it and generate these events. Then we apply the selection cuts. We know the input. We now know the output after the selection criteria, and we can obtain the efficiency. Then we have to understand the backgrounds, which are cosmogenic and neutron activation types. On this part, there were a lot of work previously done for the dark matter searches, and we just adapted those techniques in order to get our background distribution. There are many kinds of background sources, such as this radioactive isotopes, which could be present in our detector material or in the shielding or in other places, which could contribute. So that was important to figure out. So we have the simulated PDF, we have our efficiencies, and we have the background and the data. So this plot basically shows all the quantities which are required in order to get the intensity limits. The background, various sources of backgrounds are shown on the left-hand side. Much of the detailed analysis was done basically for the dark matter search experiments. And on the right-hand side, you can see on the black histogram is the data. The background model is superposed in the green. On the right-hand side of axis are the efficiencies for a particular, say, value of charge of the fractional charge carrying particle. So we have, and of course we can calculate the geometrical factor. So we have all the ingredients to calculate this intensity limit. As you can see that the background and data are comparable. And so we need to improve on the sensitivity as well as reduce the signal to background in the next sort of round of developments in order to have more precision measurements of these rare events. So with all the ingredients in place, we were able to put the intensity limit. What is shown in the y-axis is 90% confidence limit on the lip intensity. As a function of the lip electric charge, this solid line, black color line, is the new limit relative to the existing limits from other experiments previously done. There are several orders of magnitude improvement And of course, we have also, in this particular phase space of charge of lips, we have gone to larger values. One other aspect which we considered is lip flux could be attenuated as it passes through this overburden of this experiment, this rock overburden, and this may introduce some angular dependence. So what we did is we did two limiting cases, sort of. One is isotropic. It is sort of a minimal case. Because if lip passes in any other angle, it will lose more energy in the before reaching our experimental detector. The other was the cosine square theta, which reflected the distribution for cosmic muons. If you look at the right-hand side plot, this green band corresponds to isotropic limits for isotropic lips coming into our experiment, and the dashed green line corresponds to, for the same beta gamma value for cosine square theta. As you can see that the intensity goes up, the lips have lost some energy before they came into the detector. So now the next steps, as I showed you previously, the background and the data after selection criteria are comparable, so if we can improve on them. So there are some R&Ds we are doing for the next version of this experiment in order to increase the sensitivity. One is if we can lead to our detectors operating at lower threshold. So as you know, this energy deposited by lips are also much smaller compared to simply minimum ionizing particles. Further, we need to improve on the signal to noise conditions. Now, typically these detectors operate, or when a particle comes and interacts with these detectors, there are three modes of response: ionization, that is charge, or phonons, that is through heat, or scintillation through light. So these are the detection principles on which these detectors are based. And many experiments pick up their own choices of detection. Now the current generations have managed to obtain simultaneously two of these criteria. For example, Super CDMS works with both phonon and ionization. There is no technology at the moment which combines all the three. And if you have more such combination, that helps to improve on the signal to noise and the detection. So, so we have been working on phonon and ionization modes. Now, coming to some developments, this is closely happening with, leading group is of course Texas A&M. Our students are participating and trying to improve on these novel detectors. The three areas of trying to improve on, which we are currently working on, one of them we have now published the improvements, is the silicon high voltage on the left-hand side. This is a silicon detector similar to that which was used in the lips search, but due to the growing leakage current, the detectors were only be able to operate up to 70 volt. So we tried to improve on this on the silicon high voltage by reducing the leakage current. This is done by by a mechanism, the way we try to read out the signal. On the one side, if it can be made as close to contact free as possible. The leakage current tremendously reduced by 2 orders. I think it's about 10 to the power minus 16 amperes or so is the, if I recollect correctly. That allowed us, this detector, to operate instead of 70 volt, we can now, the linearity of response is up to 250 volt. and the resolution was also very good. Then there is this hybrid detector. This is dominantly worked by Himanshu Niyok. He has now completed his PhD from Texas A&M and is in Minnesota. The idea is to have a detector which will give excellent charge signals on one side, on the top, and on the bottom, the phonon signals together, so that event by event we can discriminate between electron and nuclear recoil. Doing some detailed field simulations, he came up with this structure, and there are interesting results which shows improvement in signal to noise for such a hybrid detector with different voltage conditions on the top and the bottom. The third detector is made up of sapphire. This has aluminum and oxygen content. Remember the interactions, when there are elastic interactions of the particles with this detector material, the maximum energy can be transferred in an elastic collisions when the masses are comparable. So now things are moving towards low mass dark matter search, for example. So having detectors of aluminum and oxygen, we expect a better energy, higher energy deposition compared to, for example, silicon. So this detector is also under process, and also our contacts are mostly aluminum based, so it also helps in signal to readout transfer in a better way. So here are some of the results. Of course, the setup is we have the detector, we put sources in the lab, and then there is a dilution fridge, and the dilution fridge is from NISER, and then you test it. So for example, in the silicon high voltage detectors, you can see the pulses on the lower left hand side are very well separated. The linearity of response with voltage, this is the mean of these distributions on the lower left. If one plots, then one finds a linear response almost up to 250 volt, and that's an improvement from CDMS detectors, which we managed to only operate up to 70 volt. If you look at the baseline resolution, it is roughly 1 electron hole pair in this range where there is at the high voltage where there is linearity. So these are some of the improvements we were able to make, and we reported in this paper. The below plot is improving this signal to noise separation for electron and nuclear recoil using the hybrid detector. And on the top one is what we did is we had a joint silicon and a sapphire detector together, and then we looked at the energy deposition in the sapphire detector on the y-axis versus that in the high voltage or silicon detector. As you can see that the energy deposition, if you concentrate on the box on the top, is have values larger compared to silicon in the sapphire. That's what we expected. And when you try to put in higher voltage to the silicon detector, then it gets spread out, and you can have a better separation of signal to noise and better response from these detectors. We hope that with these developments and subsequent developments of detectors, we will improve on the sensitivity of the measurements. And with this experience which we are gaining, it will be great to try and set up such experiments in India. And two possibilities, of course, all of you know. One is Jadugada Uranium Science Laboratory, which actually has a slightly less overburden compared to the Sudan experiment. And then we have the INO, which has a much better compared to what Sudan experiments had. So we are learning, in the process of learning how the detector works, how to make these detectors, and how to improve on it, how to do such analysis of rare events. With this knowledge, we can, with other colleagues in India, try and set up such things. We actually did a simulation on the neutron background for dark matter search, along with the Saha Institute of Nuclear Physics colleagues, and found that the sensitivities are comparable to some of the experiments at other places, even at the Jadugada facility. So that brings me to the summary of my talk. So when we started, we had to first really work on implementing this fractional charge particles in the GIA framework. That took some amount of time to understand almost several parts of this GIA program had to be modified. Every unit had to be understood, validated. This we did for the first time for the LIPS, and the codes are available in the GitHub. Then we went on to look at the data, and the intensity, LIP intensity limit plots, as shown on the right-hand side, were calculated from the super CDMS data. We explored a large range allowed by the sensitivity of the detector in beta gamma, in mass, as well as in charge, and put some of the lowest limits till date on LIPS intensity as a function of its charge. This, as you saw, can improve a lot if we could reduce the background and really get some counts above it. That would need these developments on detectors, and we are trying to pursue and see if we could set up such experiments here. Well, till date, it still remains a puzzle why there is quantization of electric charge and only its integral multiples of the charge carried by the electrons. So thank you very much for giving this opportunity. And we have a small group of PhD students and master students who help in moving this program ahead. Thank you.
Thanks very much, Bedanga. Wonderful talk. I mean, gave such a nice, interesting physics possibilities, addressing very interesting problems, but at the same time, so nice to also showcase some of your detector R&D efforts that has taken off very well at NISER and progressing quite well, I think. And also looking up the possibility of, setting up such within the Indian laboratory sites is something very nice to hear from you towards the end of your talk. So with that, so are there questions to Bedanga? Please, you can ask them directly, or you can type in here. By the time probably the questions come up on Zoom, there's one question from YouTube, Bedanga. It says, can quarks be lightly ionizing particles in the course of air showers?
I see. We have not seen any free quark as such, except for these QGP experiments where it only exists for a very short time. If there are such processes, yeah, but we have not seen so far, right? So,
okay. I think it is. Okay. I think it is Saurendu Gupta, right? Saurendu, is that you?
Yeah, that's right. I had a slightly out of the box question. And I see that you, as well as this experiment, as well as many other experiments, are now looking for things which are where the signal to noise ratio is close to unity, sometimes even falls slightly below unity. And of course, the detector R&D is the way all of you approach it. I was wondering whether improved statistical tools could help. For example, there are people who are working on machine learning, artificial intelligence kind of things, And since we are going to base everything heavily on Xi'an simulations, okay, it seems to me possible that you use an AI/ML system to validate, to explore better ways of extracting signal from a very noisy background. And there could be ways of querying this system eventually about what it has learned, what are the criteria it is using, and therefore build it, hand do it yourself, not just entirely depend upon the artificial intelligence system, but also understand what it is doing and then try that out as a separate statistical tool.
Yeah, so Rendu, thanks for that. I think, yes. So we have also thought on that lines. This year, a master student has joined, Aman Upadhyay. I don't know if I send him the link. So we are now using, trying to use those techniques and see if we can improve on what we have got. That's a good point.
Thanks. It will be nice to follow this in future. Thanks.
Yeah, I think, okay, just a minute. See question from Mohanty.
Yeah, okay. First of all, congratulations for a very interesting talk. I have one or two questions. My question is, as you mentioned, this fractional charge particle may be produced by the interaction of cosmic rays in the Earth atmosphere. Then you go to underground or mines to reduce the background of these charged particles which are produced in the atmosphere. So my question is, what are the backgrounds which will exist in the underground?
The background distributions, most, as you can see on the left-hand side of this, these are mostly coming from the impurities, radioactive impurities, which are there in the surrounding. The number of neutrons under the Sudan mine, as I mentioned, is about 1 per kg per year. So these sources which I saw on the left-hand side are the dominant backgrounds which are there. There are photons, there are electron recoils coming from the radioactive decays, and these has to be very painstakingly calculated in order to have a precise background information.
What's about high energy muons?
There is a veto detector put, but yes, those also form, but there is a muon veto implemented in the experiment to try to remove it.
See, if you are okay, that's fine. If you are cutting off all the cosmic ray background, so then we are saying these are these fractional charge particles are produced in the cosmic ray interactions, but then we are cutting off all the background. So then how do you say that these are produced by the cosmic ray interaction?
The veto is inside the detector in the kavan. So it's not that they are not coming in. In the detector, it is not that before they come into the kavan, they are all stopped. It is not stopped, it is vetoed out. To as extent as possible. Also, we try to look at their signal pulses coming from such contributions and try to remove them. Yeah.
Okay, so these are maybe primarily muons, right? High energy muons, which are vetoed, and this muon interaction that could have produced to these fractional charge particles, which you are trying to detect, which are
what we are talking about is cosmic ray muons and Earth atmosphere. If they have interacted, like for example, you have in normal colliders. So such
Okay,
interactions can happen in the atmosphere and the lips can come in. There is one possibility.
Okay. But they do not interact by ionization.
Yes.
HCs. Okay.
Yeah,
So don't they get absorbed by this large overburden?
they do.
Okay. Okay. But there will be still some probability they can go to your underground, right?
Yeah, if they are highly energetic enough, possibly they will reach us.
Okay. Okay.
Hello?
Thank you.
Sorry, I think I had some internet issue from here.
Yeah.
I think Professor Vivek Datar probably wanted to ask some question.
Can you hear me, Vedang?
Yeah.
Okay. My question is, you mentioned the possibility of the JUSL, but the present, I think, lab is at minus 550 meters depth. Since your detector is not very big, or at least it's not as, I mean, maybe it cannot be fitted in that lab, but is there a possibility of putting it at minus 880 meters in JUSL?
Yeah, that we have not explored. You have rightly said. Also, one more thing we have to do some background measurements. What we did was simulations, but we need to do some measurements in this uranium mine.
Yeah. There are some already existing, right? I mean, Satyajit
Yes,
Saha's group have done
yeah.
some measurement, but maybe you require more things to be done.
Yeah, whatever what they measured, the SNP group went into, part of it went into this paper, but that was not sufficient.
Yeah.
I learned that Tilak also did some experiment recently, so
Yeah.
we can talk and see if that's possible.
Yeah. Because then the time scale might be, fairly small. I mean, you could probably rig up something fairly quickly and do a competitive measurement. The other thing I wanted to ask is, can this detector be scaled up? Can you put, let's say, 10 of these detectors, or each of them has to be cooled and therefore you don't have the cooling capacity?
No, yeah, we would need this dilution freeze to do that, but it is possible to scale it up, and so these are let me also tell you the technology for this is coming from Rupak Mahapatra's group in Texas.
Yeah. Mm-hmm.
And I was talking to him. He says it is possible to scale up and set up. There are some cost estimations we are working on, so that to know how much it would be. But
in the dilution refrigerator that you have, is it possible to stack up a few of these?
Yes. Or even otherwise, as you saw in Super CDMS, let me just show you. The fridge could be here, and then there will be a cold finger which leads to the cooling for the detector volume. But of course, that would need some amount of more work to put in place. Yeah.
That's right. Okay. Anyway, it was a very nice talk. I attended only the latter part of it, but anyway, it was very nice. Thank you.
Thank you.
Okay. Are there any more questions to Bedanga? There's a comment from Vandana. That's very nice. Look here. Yeah, I think I just a minute if I can. Yeah, I think there are no more questions, Bedanga. So thanks once again. Thank you very much for your nice colloquium, and all the best for your future, detector R&D activities, and also hopefully a bigger deployment of these detectors, as Professor Datar mentioned. So thank you very much once again for this wonderful colloquium. Thank you.
Thank you for giving this opportunity. Thank you.
Thanks. Oh, great. Yeah, thanks. Bye.